All right, so free frames. So free frames, like what we applied earlier. For example, this is before the allocation, and we want to apply, okay, the following pages here, page 0, 1, 2, and 3, onto the physical memory. So we have to refer on to the page table, of course. All right. So in here, okay, larger page size wastes more memory, but more efficient in terms of overhead. Okay, so modern trends have been to increase the page size, and in some systems even have multiple size pages to try to make the best of both worlds. Okay, so the page table entries, frame numbers are typically 32-bit numbers, allowing access to 2 raised to 32 physical page frames. Okay, so if those frames are 4 kilobytes in size each, so that translates to 16 terabytes of addressable physical memory. You can't imagine that, 16 terabytes addressable physical memory. All right, so that's 32 plus 12 is 44 bits of memory address spaces. Okay, so when a process requests a memory, free frames are allocated from a free frame list and inserted into that process page table. Okay, so process are blocked from accessing anyone else's memory because all of their memory requests are mapped to their own page table. Okay, so there is no way for them to generate an address that maps into another process memory space. So if you have a process space if you have a memory space for a process, then that should only be used by that process. Okay, so the operating system must keep track of each individual process page table, updating it whenever the process pages get moved in and out of the memory, and applying the correct page table when processing system calls for a particular process. All right, so same thing. Where do we plot page 2 here? So page 2 is on 18. Okay, where do we plot page 0? Page 0 is on 14. So page 0, you've got 14. So you've got that mapping. So initially everything is a free space. All right. Slide 41 of 71. What time is it? 8:44. All right. So implementation of the page table. So page table is kept in the main memory. So we are using this page table base register, or the PTBR, points to the page table. You've got the page table length register, or PTLR, indicates the size of the page table, right? So in this scheme, every data or instruction access requires 2 memory accesses, right? One for the page table and one for the data or the instruction. Okay, so the 2 memory access problem can be solved by the use of a special fast lookup hardware cache called translation lookup aside buffers, or the TLBs, also called the associative memory. So again, we are discussing a different techniques used in memory management and modifying or innovating the existing methods here. Okay, on the translation look aside buffer, so some TLBs store the address space identifier, or ACID, in each TLB entry. Uniquely identifies each process to provide address space protection for that process. Okay, so TLBs typically small, 64 to 1024 entries. Okay, so on a TLB miss, value is loaded into the TLB for faster access next time. So replacement policies must be considered. Some entries can be wired down for permanent fast access. Okay, now the hardware support for that. Okay, so page lookups must be done for every memory reference, and whenever a process gets swapped in and out of the CPU, each page table must be swapped in and out too. Okay, along with the instruction registers. So it is therefore appropriate to provide hardware support for this operation. So in order to make it as fast as possible, and to make process switches as fast as possible also. Okay, so one option is to use a set of registers for the page table. Okay, so for example, You've got the old DEC PDP-11, which uses 16-bit addressing and 8 kilobytes pages. So resulting only 8 pages per process. So it takes 13 bits to process an 8 kilobytes of offset. So leaving only 3 bits to define a page number. All right. So now this is the paging hardware with TLB. So what was added here? You've got here the TLB. Okay. So the TLB was added on the hardware. Again, why do they have just to? Why did they have to innovate this for faster processing? That's the only purpose here. All right. So to come up with the address on the physical memory, so we have now two tables. All right. So one with a TLB, okay, and you've got the existing or the previous page table used. So they combined TLB with the page table. Okay. Now, effective access time. Okay. So assuming the hit ratio, percentage of times that the page number is found on the TLB, an 80% hit ratio means that we find the desired page number in the TLB 80% of the time. Suppose that 10 nanoseconds to access the memory. So if we find the desired table or page in the TLB, then a map memory access takes 10 nanoseconds also. So otherwise, we need 2 memory access so that it is 20 nanoseconds. Okay? So to compute for the effective access time, all right? So EAT, that's 80% times the 10 nanoseconds there, okay? Times the 20, okay? Times the 20 nanoseconds there, okay? Okay, that is equals to 12 nanoseconds. All right. So a TLB hit takes 12 nanoseconds. So with 80% TLB hit ratio, the average memory access time would be this one. Okay, so which is 12 nanoseconds. For a 20% slowdown, all right, this 20% here, okay, so for a 20% slowdown, to get the frame number, so a 99% hit would yield to 10.1 nanoseconds. All right, 99% hit ratio would yield to 10.1 nanoseconds, implying only 1% slowdown in an access time. All right, so at a 99% hit rate would yield to 10.1 nanoseconds average access time for a 1% slowdown. That's fast. All right.